Ja, guten Abend, meine Damen und Herren. Herzlich willkommen wieder zu Space at TU Darmstadt. Ein ganz herzliches Grüß Gott auch zu unserer Vortragenden, der Chiara Manfletti. Und ich darf auch begrüßen den Herrn Professor Bruder, der uns noch ein kleines Grußwort sprechen wird. Die TU unterstützt die Veranstaltung immer sehr, dafür sind wir sehr dankbar. Und er hatte eigentlich vor, zu Beginn der Veranstaltung auch eine Begrüßung zu sprechen, aber da war er leider in Berlin am Boden gegroundet, sein Flugzeug ging nicht und er musste das dann leider absagen. Umso mehr freut es mich, dass es heute klappt. Ganz kurz noch zur Organisation. Wir sind heute schon im letzten Termin angekommen. Nichtsdestotrotz habe ich Ihnen die Flyer nochmal ausgeteilt, aber andersrum, ich möchte Sie nämlich einladen, schreiben Sie was drauf. Wenn Sie eine Idee oder einen Wunsch haben für ein Thema, das wir in einem zukünftigen Kolloquium aufgreifen sollen, sind Sie so nett, schreiben Sie es drauf und geben Sie es nachher hier ab und wir versuchen das so weit möglich zu bündeln und dann in ein Thema zu akkommodieren. Vielen Dank hierzu schon. Ja, und jetzt darf ich das Wort kurz an Professor Bruder übergeben, bevor wir dann tatsächlich einsteigen.
Ja, ganz herzlichen Dank, Herr Bertrand, liebe Frau Manfletti, liebe Angehörige der TU Darmstadt, liebe Studierende, liebe Gäste. Ich will Ihnen nicht viel Zeit wegnehmen und Herr Bertrand, Sie haben es ja schon gesagt. Eigentlich war mein Ziel, Sie zu begrüßen zu Beginn der Veranstaltung. Das gehört sich auch so, weil wir freuen uns, das haben wir auch bei der ersten Serie gemacht, wir freuen uns wirklich sehr, dass es diese Veranstaltung gibt. Und Sie haben es gehört, ich hing in Berlin am Flughafen fest. Eigentlich könnte man das ja sagen, passt ja wunderbar zu dieser Veranstaltung, weil diese Veranstaltung aus unserer Sicht ja darstellt, wie Technologie wirklich schwerwiegende Probleme löst. Menschen kriegen es hin, dass man bis zum Mond fliegt, Menschen kriegen es hin, dass man eine Station im Weltall baut, wo man andere Menschen pünktlich hinfliegt und die genau zum richtigen Ort, zur richtigen Zeit am richtigen Ort sind. Das kriegen alles Menschen hin, aber sie schaffen es nicht, eine Maschine von Berlin nach Frankfurt zu bekommen, sodass sie pünktlich ist. Aber das wäre der Einstiegsgeld gewesen. Aber was ich eigentlich gelernt habe, und ich glaube, das ist das Interessante dabei, der Grund, warum ich nicht herkommen konnte damals, war ein schlicht und ergreifend ein Unwetter. Es war einfach ein natürliches Ereignis. Es hatte gar nichts mit Menschen zu tun, sondern einfach die Natur hat gesagt, jetzt nicht fliegen. Und das fand ich sehr demütig. Ich glaube, das ist das, was ich immer verbinde mit dem Thema Weltraum. Man wird unglaublich demütig, wenn man nach oben kommt. Und das scheint aber irgendeine Faszination zu sein, diese Art von Demut. Ich habe bemerkt momentan auch alle, was es heißt, demütig gegenüber der Natur zu sein. Der eine oder die andere kriegt mit, dass gerade junge Menschen in Thailand gerettet werden. Ich weiß nicht, wie es ihnen geht. Man sitzt als Mensch davon, das kann doch gar nicht sein. Das muss man doch hinkriegen. Das muss doch möglich sein. Man fliegt ja sogar zum Mond. Aber manchmal kommt man an die Grenzen. Und das, glaube ich, ist ganz oft, wenn es um das Thema Weltall geht. Also uns freut das außerordentlich als TU Darmstadt, dass wir ein so hochinteressantes, so aktuelles, so faszinierendes Thema hier in Darmstadt gemeinsam bespielen können. Ich glaube, das ist etwas, was oft vielleicht gering geschätzt wird, dass eine Konstellation da ist, in Darmstadt mit ESA, einen Partner zu haben, hoch ausgewiesen im Feld, und mit der TU Darmstadt vielleicht auch einen Partner für die ESA zu haben, mit dem man gemeinsam interessante Themen bespielen kann. Also beste Startvoraussetzungen. Wir haben es in der Vergangenheit genutzt und ich glaube, auch im Namen von ESA sprechen zu dürfen, eigentlich noch viel mehr vor in Zukunft. Ich glaube, wir sind jetzt an einem ganz guten Punkt angekommen. Wir haben eine große Unterstützung in der Lehre, da werde ich gleich noch ein, zwei Sätze dazu sagen. Wir haben Lehraufträge aus dem Bereich, mit Ihnen, Frau Manfletti, mit Ihnen, Herr Bertrand, mit dem Herrn Manfeld, haben wir zusammen mit Herrn Landgraf zusammen haben wir Lehraufträge. Wir sind in der Forschung unterwegs, werden es sicherlich mit ESA-Lab der TU Darmstadt noch verstärken. Wir sind in Gründungen unterwegs, wenn es um das Thema geht, Ausgründung aus der TU Darmstadt in Gemeinsamkeit durch Cäsar unterstützt noch zu fördern. Es gibt eine ganze Reihe von Dingen, die uns umtreiben, wo wir noch sehr viel zusammen tun können. Und das jetzt vielleicht der Abschluss auch für heute, zeigt sich, finde ich, mit diesem Kolloquium Space at TU Darmstadt besonders gut. Und was wir merken, es scheint ein breites Interesse zu fruchten, sowohl bei Studierenden als auch bei Gästen, auch bei ganz jungen Gästen, die vielleicht auch dadurch erst neugierig gemacht werden für Studium und Lehre an der TU Darmstadt für Forschung. Also das passt hier sehr gut hin, ohne jetzt jemand persönlich zu nennen. Also es passt sehr gut, so ein Kolloquium zu machen, aber es braucht auch helfende Hände. Und insofern passt es vielleicht gar nicht so schlecht, Herr Bertrand, dass ich zum Abschluss der Reihe nochmal hierher kommen konnte, weil das, was Sie sicherlich auch am Ende machen werden, zu danken, möchte ich aber übergeordnet tun und ganz herzlichen Dank an die ESA und ESOC, an Ihre Kolleginnen und Kollegen, die uns unterstützen, die schon da waren und ganz ausdrücklich und persönlich Ihnen, Herr Bertrand, wirklich meinen herzlichen Dank, dass Sie das immer wieder auf sich nehmen. Wir beide wissen, das ist in der Organisation nicht immer ganz einfach. Sie nehmen das immer sehr gelassen und haben eine ganz tolle Veranstaltung. Mich freut es sehr, dass wir Sie als Kooperationsprofessor jetzt bei uns haben. Also persönlich mein Dank. Auch an unsere Hochschulgruppe, die das unterstützt, TU Darmstadt Space Technology. Auch ganz toll, dass Sie sich das immer wieder vornehmen. Ich weiß, dass es viel Arbeit ist, neben dem Studium. Super, dass Sie das machen. Der Erfolg gibt Ihnen recht. Unseren Vortragenden ganz herzlichen Dank, auch dem Fachgebiet von Kollegen Klinghoff, vom Prüfsystem und Regelungstechnik ganz herzlichen Dank und Ihnen, dass Sie hier sind. Auch das immer an einem Montagabend hierher zu kommen, die beizuwohnen und die große Zahl freut mich sehr. Das soll es gewesen sein, damit ich Ihnen nicht so viel Zeit von dem eigentlich Spannenden heute wegnehme. Ich wünsche Ihnen viel Spaß und ich freue mich schon auf den dritten Durchlauf. Herzlichen Dank.
Ja, jetzt muss ich doch noch ein Wort zu unserer Vortragenden sagen, die Chiara Manfletti. Wir haben in ESA so einen Online-Messenger. Wenn man sich da einloggt, dann kann man so Chat machen. Ja? Und wenn man da die Chiara sieht, dann steht da dran, anzutreffen nach der Heisenbergschen Unschärferelation. Die Ingenieure, Physiker, die wissen, was das heißt. Ja? Das ist das gleichzeitige Kenntnis von Ort, Geschwindigkeit und Zeit. Das ist nicht so einfach. Die Chiara ist sehr viel unterwegs. Sie ist Programmberaterin zum Generaldirektor, hat zurzeit sehr viel zu tun. Wir bereiten uns auf die Ministerratskonferenz nächstes Jahr vor und die ganzen Programme müssen jetzt vorbereitet und in eine Form gebracht werden. Und das ist alles bei ihr auf ihrem magischen Rechner und natürlich in ihrem Kopf drin. Ja, so wie auf dem Messenger ist auch ihre Vita. Ich möchte nur kurz ein bisschen einen Einblick geben, weil ich finde es total spannend. Geboren in Mailand, dann Abitur an der American School of Milan, Studium Aeronautical Engineering, Imperial College London, dann Master of Space Studies an der International Space University Straßburg. Also Sie sehen, es war schon damals nicht so ganz einfach, den Ort eindeutig festzulegen. Dann aber mehrere Jahre am DLR-Institut für Raumfahrtantriebe in Köln, dann Gastwissenschaftler in Tokio University, Japan, wissenschaftliche Mitarbeiterin in Lampolzhausen, Institut für Raumfahrtantriebe und dort auch promoviert zum Thema transientes Verhalten und Modellierung von Flüssigraketen, Triebwerkskomponenten und dann Gruppenleiterfunktion, dann im DLR Leiter der Vorstandsberatungsgruppe und jetzt seit einiger Zeit direkte Beraterin vom Generaldirektor. Unheimlich spannend, ich freue mich auf den Vortrag, Chiara.
Herzlichen Dank. Guten Abend. Ich hoffe, es stört niemand, wenn ich jetzt auf Englisch wechsle. Und das will ich jetzt dann auch einfach machen. Bevor ich das aber mache, eine Frage an alle. Kennt ihr diesen Ausdruck? Has anyone heard about this before? Yeah? Okay. Leo as halfway to the rest of the universe. What do you think that this means? To me, this means various things. It means there's physics behind it, but there's also a part which is about dreams. And what I want to do today is start a bit in the future, so talking about a little bit about dreams, and then come back to the present, see where we are today, and then discuss a little bit of what we need to be doing in order to actually get there. So again, what does this mean? It means indeed that Leo is halfway to the rest of the universe. If you look at it from a physical point of view, this is sort of a metro map to the universe in terms of delta V requirements. For those of you who don't know what the delta V is, it's the actual velocity change that we need to get from one point to the next within our solar system. To get, for example, to Leo, we need about 8 kilometers per second, starting from the surface of the Earth. And if you see going to, for example, if you sum up the delta V's to go to the sun, I think it's about 30 kilometers per second. So indeed, if you look at this map, you see that Leo is not halfway to the rest of the universe, at least not in what the actual physics is concerned. But there is a difference between what we have in Leo and what we have and the rest, and that's we have an atmosphere, we have to get out of this atmosphere, we have to get into Earth orbit, and then from there we can take it to other planets, we can take it to moons, we can take it to the solar system, or we might find atmospheres or not. So indeed, Leo is in a way halfway to the rest of the universe because the environment is quite different. And this is what I wanted to say. If we think of space as sort of noble, and not just we are on Earth and there's something out there that we could be doing, and we think of different nodes in space. We think of one node being in Leo, one could be in Geo, one could be in the Moon, one could be, I don't know, around Jupiter or Ganymede, whatever else. We can then also think of things that can happen between one node and the next. So we don't transport from just the Earth's surface to Leo, the Earth's surface to Geo, the Earth's surface to the Moon, but we transport from one node to the next. And we have services at these different nodes. We have services that can be, as you see here, cargo and human delivery, dispatch, return from space, but we would also be doing maintenance, inspection, life extension, assembly, and upgrade. We could be storing things, we could be providing support for human presence, we could be doing observations, navigation, telecommunication services, which would be required for doing things, for example, if we are in lunar orbit on the surface of the Moon. We could be relocating assets from one node to the next, or amongst the nodes, or in one node from one location to the next. We could be rescuing or recovering things, or even people. And we could be doing removal of debris or things which are no longer active. So these are all sorts of assets and services that we could have in these different nodes. And this is a bit where I would like to take you in the future. So if we stop thinking of us just being on Earth and doing something from Earth to somewhere else, but if you will, Earth just being one of the nodes. And now if we go to what we already have in space, and we sort of start thinking of these things. We have Earth observation that we do, and we have very many assets in space that we need for doing science, for doing meteorology, for providing services to other sectors, which we provide through Copernicus. We have indeed telecommunication and satellites, and these provide communication. These are all assets that I'm sharing with you. And these assets we could think of having also these other nodes. We could think of having optical communication from Leo to the Moon, or from Leo to Jupiter. So again, not just thinking of the things we have today, but of things that we could be doing in the future. We have an ISS, and ISS is not just a mini satellite or just some small assets. It's been up there for quite some time, and it's something that we need to maintain, service, refurbish, inspect. Where we could think of maybe reusing it someday. And indeed, we do perhaps Earth observation from ISS, and we could think of doing more with such assets in space. I didn't put any pictures up about hotels or things like this, but people have thought of these things in the past, and why not engage in these things as well in the future? That our thoughts sort of wondered what things we could do. Indeed, if we look at our exploration, there are some considerations of long-term exploration scenarios that we could engage with on the surface of the Moon. And if you look at these things, they don't just consist of single one-off assets, but they consist of things that we reuse, like, for example, landers that you see right here that would go up and down from a gateway that you'll see in a second, and bring cargo samples, but even humans, to different points of the lunar surface. Indeed, I don't know if many of you look at the web and follow a bit what the exploration strategies are that we are engaging in with the US, but the Lunar Orbital Platform and Gateway is part of this exploration strategy. The idea there is to not have just another ISS around the Moon, but having indeed a platform that will allow us, it's sort of a pit stop, again, this nodal approach. A pit stop that will allow us to go down from it and approach different parts of the Moon so that we can do all sorts of different types of activities, from in situ resource utilization to science to all sorts of other things. And we need to be addressing a number of challenges to actually get there. One of the things that I find most exciting about the Deep Space Gateway is the Esprit module. And why do I bring this up there? There's other modules as well. Of course, there's the habitation module with life support. Of course, that's extremely important. But this one, for example, provides airlock, and it also provides specifically some capabilities for refueling, and I think this is actually one of the most important activities that also need to be done if we really start thinking about nodes, where we have fuel depots in space, and where we produce fuel on other planets, so all these sorts of things. And I'll get back to this point as well later. One of the things we're looking at is the hierarchies architecture, where we would have, together with our Canadian colleagues and our Japanese colleagues, a sort of modular approach with a descender. We would have a rover, a long-range rover, and then we would have an ascender, so that we could repeatedly go on the surface of the moon and do all these wonderful things. We would have a robotic precursor, and then we would have a human precursor. And there we have to think of reusable propulsion. What does it mean to have reusable propulsion? Can it be also sort of a low-cost reusable propulsion? What does this all mean? We could think of a lunar tug based on electric propulsion, some advanced electric propulsion. I just approached the topic of electric propulsion at my last lecture on Friday, and I was showing my students the fact that the electric propulsion nowadays have just very low thrust, so at the moment it's not mature enough to do these kind of things. But if we imagine one day to be able to go to Mars in just a week, or to the moon in just an hour, what would this take? And Arnold can certainly also tell us what it would take in terms of orbital mechanics. We would then have to build things, and so we would need some in situ resource utilization capabilities. But what if we also sort of took what assets we have in space and we were sort of to recycle them, reuse them, reprocess them, extract valuable metals and do something out of it? I know it sounds a bit like science fiction, where we can't even master today the in situ resource utilization techniques, let alone sort of try and produce or recycle something in space. But I think we need to consider these things. If space indeed is an asset that we want to use to its maximum, we shouldn't forget, however, also that space requires ground infrastructure. Is certainly the most important point. And space protects, however, also infrastructure that we have on the ground. So we also need other assets that monitor space, because it's a harsh environment. This should never be forgotten. We can dream, but we shouldn't forget that we have limits. We're humans. We require certain levels of G. We don't really like high radiation levels. So we need protection, and we should take care of it. So what is my main message? My main message to you is space is infrastructure, and to this infrastructure we need to be doing all sorts of things. We need to install, we need to continue this infrastructure, we need to maintain it, upgrade it, and do everything else that we do with just normal infrastructure. The first time I spoke about infrastructure in space being a critical infrastructure at ESA, I was actually booed. I said, no, don't talk about critical infrastructure. This is difficult. It's about responsibilities and roles within Europe. So then I said, okay, it's an infrastructure which is critical. If it's not a critical infrastructure, then it's an infrastructure. I said, okay. But indeed, if we now think back to the word reusability, and Arnold first asked me, what is the topic that you want to talk about? I picked reusability because when I was listening to Jan's first speech, one question came up about reusability, and I thought, man, I can deal with launcher, I can talk about reusability. But then I realized reusability is so much more than just launchers when I was coming down to making this set slide. So again, what does reusability really entail for space? Are we just talking about launchers, or are we talking about more? We had a CDF session with some industrial partners so that they could actually tell us when we speak about in-space servicing, the whole topic of servicing assets in space. What would they think of possible activities? And I know it's a bit small, but you can read some of the things. Maneuvering a satellite from MEO to MEO, perform some debris removal mission, perform multiple debris removal missions, inspect. So you see that industry came up with a whole list of things associated to servicing of space assets, requiring, of course, other assets, and they give it a ranking. Oh, we don't have to go into the ranking, but you'll see there's a whole list with several pages. And I wish we had the money to do all of this. That would be really great. So going back to my original question, is it just reusability of launchers that we're talking about? And when we think also reusability in space, let's also think of what we mean when we talk about reusability on Earth. If we compare plastic bottles and glass bottles, somehow they're both reusable, One is reusable as is, glass bottle. Some are reusable, like a plastic bottle, but they have to go through some processing before they're reused. So is it a first degree or is it a second degree reusability? So indeed, we have reusability of launchers, of satellites, of components, of materials, even of orbits. So we have to even clean up our orbits. And again, reusability entails reuse, recycle, refurbishing, maintaining, upgrading. So this is, if you will, the picture that I'd like to paint for you regarding the future and what actually reusability entails. So the question then comes up, where are we today in these grand hotels and recycling factories in space? And the picture, I must say, is not so good. But anyhow, let's see where it is. We've done, in terms of launchers, lots of studies. We've thought of doing re-entry vehicles. We've thought of having flyback boosters for Ariane. We've started doing experiments for hypersonic re-entry bodies, the IXP. But I must say there isn't much that is going on. So the question is also why. Now, if we look at the Ariane 5, and this is the Ariane 5G Plus version, which actually took Rosetta on its wonderful trip, well, you'll see it's a huge beast. It weighs 730 tons. It's 46 meters high, and it has a payload of 1%. So it's a huge beast which carries, in theory, not very much to orbit. And it has solid boosters, which have most of the thrust. It has a cryogenic main stage with a cryogenic engine, which you can't really see, it's right here at the bottom. And then it has a liquid upper stage. And you see here the percentages of contributions of the various components to the whole 730 tons. Now, if we look at the trajectory of it, we will see that it separates the boosters at a certain stage. We call it actually a 2.5 stage vehicle because the boosters separate relatively early and because the central stage is burning while the boosters are also burning. And this separation takes place at about 60 kilometers height, which is already quite high, and they're actually going quite fast already. And then at a certain stage, when we're out of the Earth atmosphere, the fairing separates because we want to get rid of the additional structural mass. So we're trying to optimize the mass that we're actually putting into orbit. But despite all these efforts, the payload that we actually bring into orbit, depending, of course, on the orbit that we want to bring it in, is not that much. And then if we look at the details again as well, we will see that there's certain velocities and loads associated with this trajectory. It's not just a happy ride, it's quite a trip. The velocities associated with the separations are quite high. If you look here, you'll see the first separation, the second separation, etc., etc. And you'll see that we are reaching Mach numbers which are quite high. And when we re-enter, of course, this will mean extremely high energies that we will have to break down in order to arrive at the surface of the Earth unbruised so that we can actually reuse something. So perhaps reusability, at least for Ariane 5 and its components, is a bit difficult. And then the other thing, obviously, is what are the loads on board? The loads, if you see here, for example, just the accelerations. These are the acceleration profiles that the launcher goes through the booster burn, after booster separation, the first stage continuing, and then after the second stage finishes burning, we see here the third stage. And we see that we have quite high acceleration peaks that can go up to almost 4.5 G, which is quite a bit. But of course, these loads we try to restrain them so that the satellite doesn't suffer too much. In addition to these, we have shock loads, we have vibration loads, we have acoustic loads, we have all sorts of difficult environment. And now, if we again go back to the thought of reusing and recycling, there's an additional thought that comes into mind. Of course, access to space is probably one of the most expensive components or contributions to actually doing space. But the other thing is, of course, that when we design things on ground, they have to withstand launch loads. And when they're in space, they don't experience these loads anymore. So part of the difficulty in the design is that they actually have to withstand loads that they only experience for a couple minutes, and then that's it. And maybe they're in space for 15 years. So again, we see the idea, there is some attractiveness to actually producing in space and recycling things as well. If we look at the trajectory of the Falcon Falcon 9 looks somewhat different. It's also a completely different launcher. It's a two-stage launcher with liquid engines in the first stage, and one single liquid engine in its upper stage. The boosters, as you see here, either fly back to the landing basically place, or they fly downstream to some barge. And depending obviously on the trajectory they fly, they will experience different loads. But the loads experienced by this first stage of the Falcon are a lot more moderate than the loads that, for example, Ariane experiences. Now, I don't know if the slides are distributed, but I hope so, because I found this, and it's actually very interesting, but we can't go through it in detail. But what it does, it shows you the loads that the Falcon 9 first stage goes through. And what you see through this, indeed, is that when you can think of reusing the first stage of Falcon, because it doesn't reach those high Mach numbers, and it will allow you to bring it back down so that it does survive sort of the soft re-entry. With Ariane, the central stage of Ariane is a lot more difficult because it reaches higher altitudes and because it has a sort of a higher Mach number associated. So again, I hope the slides are distributed so that they can have a look in detail. Yeah. So then the question is, okay, we've spoken a little bit about the possibility of reusing or flying back the central stage. Can we think of reusing and flying back an upper stage? There have been concepts, for example, this is one of the concepts where you sort of fly back head first, and then again you apply some negative thrust and then land vertically. It's actually quite interesting concepts that SpaceX has also considered for its upper stage here, even more detailed future of it. But they haven't implemented yet, and we'll see later perhaps why. But again, these are things that we can think of doing, and the question is, why do we sometimes implement reusability and why don't we? Another thing that SpaceX has done is they've developed a weird boat with some weird arms. I don't know if you've seen this. They have nets in the middle, and with this net they want to try and recapture the fairing, which you'll see they've slightly modified right here. This is a sort of a previous version of their fairing. They've modified their fairing by adding some small thrusters, and the thrusters, they break it down so that it's slow enough that it then will survive the re-entry because it's so big, it doesn't weigh that much. And by that, they hope to recover about, I think it's about 6 million per fairing. So apparently, this weird process and this boat and infrastructure cost they have are good or enough to compensate the cost of recovering the fairing. This is another type of reusability, but it's not reusability for access to space, it's just reusability for access to sort of suborbital heights for doing either tourism or research. And this is what Blue Origin is doing. I find this personally quite exciting because it's also reusability that they do with liquid oxygen and hydrogen, something that in Europe we always kept on saying is very hard because hydrogen entanglement. Hydrogen is a very small molecule and will sort of go into the creeps of materials and enribble it. And so hydrogen enribblement is a bit of a problem for applications where we have higher pressure and higher temperatures. But they're doing it and they're quite successful, and I'm sure there will be a competition to SpaceX at a certain point with a reusable launcher, certainly for their first stage. One of the most interesting capabilities, of course, is that one engine which allows them to sort of deep throttle so that they can soft land. And so tap-off cycle, weird cycle, I won't go into the details, but it's a cycle that no one's ever flown before. So they have a deep throttable engine, it's completely new technology, and it works, it's quite fantastic. And this is one type of reusability. Then we have, of course, also Spaceship One. Again, this is also, in a way, reusable. It's again for touristy purposes. However, I mean, if you look at it and you see it already, it's quite good in terms of propellants it uses, but it's hybrid. So hybrid, as you can imagine, has only a limited reusability. Hybrid is a case where you have a solid propellant and a liquid propellant, and then sort of the two burn together, and you can sort of change the thrust of the engine by controlling the mass flow of the liquid propellant. but still, somehow you have to reprocess the one component that is in solid form. And it's quite difficult, but it is some sort of reusability. Dream chaser is another concept which is reusable as well. It's sort of an upper, it's supposed to be a replacement for an upper stage of an orbit vehicle, which then comes back down. It launches on top of a normal launcher, just as a payload. We're considering of launching it out with an Ion 6. But this is also reusability. And then the question, of course, is this better reusability than we had with the shuttle, where they, after each and every launch, they had to change the panels for the extreme cost and energy because of reusability, especially in the case where we had humans, because of the runners that we had humans on. X-37B, this is definitely something which is also reusable, but we don't really know what the Americans are using it for. Again, it's an upper stage vehicle which stays in orbit, moves from one orbit to the next, and does some activities in spying or also night but this is also, and there are certain hybrid versions also. Our setting here is supposed to have a minimum of 5 reuses, and the idea behind that is that we can do in-orbit validation, demonstration, and even microgravity research. So this is the way we are engaging in reusability at the upper parts of the access to space. And then we have the more complicated things that never really happened, that we've looked into, at least worldwide. Venture-Start is one such concept. And this is single-stage orbit. So now I'm moving to the more, and I said, the more advanced or crazy concept. Single-stage orbit, like Venture-Star, the Delta Clipper, where the difficulties here, of course, are taking the whole mass of the actual mass of the structure up to orbit, right? So we were seeing that both with the ION as well as with SpaceX, we had several stages to get rid of that structure. Here they're actually taking everything upward. Then we have scramjets, advanced engine concepts where we have supersonic combustion going in, taking place within the engine, where we have a complex shock system to enable us to have enough mass flow going through here so that we can produce sufficient thrust, and where this huge engine becomes sort of a part integrated in an even bigger vehicle. Obviously these big vehicles are associated with big structures that, in order to fly, have to have a low structural index. In order to get these low structural index, we need to have advanced materials, which we don't have at the moment. So we keep on trying, but we're not there yet. The Skylon is another such concept, where we have a combined cycle engine with a completely complex air breathing system with an extremely fantastic and complex heat exchanger based on helium, which then feeds for stage combustion rocket engines. Extremely complicated cycle, and but we're working on it in Europe for either a single stage to orbit, but now we're thinking of a 2-stage to orbit version, which is perhaps a little more easily done. And you see that there are many countries which are interested in being involved. And we from ESA side are trying to push this concept forward because we believe that it's either now the moment to talk about hypersonics, or at least worldwide we'll miss this train. We will be doing some tests of the actual core part, which will include the heat exchanger and the power pack, pumps and the gas generator on the rocket engines end of 2020, and then hopefully this will continue on, but we'll have to see. So now I get to another question. So yes, but what is the driver? What's the driver behind reusability? I always say reusability in and of itself is either a dream, so it's like the holy grail of people in space, or it has to have some other driver. We can't just say we want to do reusability because it's cool. So is it to have a competitive launch price? But if you want to have a competitive launch price, there might be other alternatives to actually getting it. You don't necessarily have to reuse. So we really have to ask these questions. And how do we get competitive launch prices? We could, at least from an industrial point of view, we could have public subsidies. At least from an industrial point of view, that works. We have to see if countries are happy to provide that, but that's one option. We can increase the cabins. In space, we have numbers which aren't exactly high, so we produce more like prototypes, or we produce 10 a year, so that we can try and increase the cadence so the prices go down, and I have a picture about that in a second. Or we can try and indeed lower the costs of the things that we do. And how could we do that? We can have new production methods. 3D printing is certainly one that could help us. We certainly could think of reusability as being an option, but we then have to look at the exact industrial setup, etc., etc. We could think of having completely new systems which are simplified based on the number of components that they have. If we look at our European engines, they're beautiful engineering marvels, but they're really quite complicated in terms of how they're designed and how they're built. We could introduce also new assembly methods. I've explained to my students that, for example, with the Vulcan, it has 500 plus injectors, and these are all manually screwed into the faceplate. This is going to obviously take time, and it's going to cost lots of money. So we can try and find advanced mechanism of even manufacturing these engines. And if we go back to reusability, we can think of sort of either having some hybrid system or indeed single stage to orbit. We could have stage returns, as we've seen with SpaceX. We could have even just recovery of perhaps the most valuable parts of the launcher, like the engines, if indeed that's the most expensive part. And then we could sort of think of either flying back or having some throttling capability of the engine, or a parachute, or in-air capturing, or a combination of them all. So the driver at the moment is the cost of access to space. There is no other way to go about it. This is a bit of an old plot, but it shows you two important lines. The line where we sort of are now, or we were in the recent past, of $20,000 per kilogram of the cost of access to space, and the line of $10,000 per kilogram of payload in space. And this is the line where we want to get at in the near future, and I want to probably even go further down. This is a plot that shows you the percentage of the price of a component on a Falcon 9 launcher relative to the whole launcher price. Okay? And it's important that I have the word price in there, not cost. We don't really know what the launcher costs. We have no idea. But we see what the market prices are that SpaceX, for example, is offering. And we know what the market prices are that SpaceX is offering to both commercial entities and also institutional entities. Based on that, we can sort of try and estimate what the cost is, but we don't know for sure. So what you see here indeed is that the first stage is more than 50% of the price of the whole launcher. So from a SpaceX point of view, it certainly makes sense to try and recover this first stage and reuse it, because if then the refurbishment that goes into requalifying it is minimum enough, then theoretically he could save up to 50% of the price of his costs. So this certainly makes sense. The second stage we see is not as much, and this is part of the reason why the efforts into reusing the second stage, which on the one hand are also a lot harder because of the fact that you have the difficult environment of re-entry, but also you see the advantage of getting the stage back are not quite as high. Now this might be extremely specific to SpaceX and the way it's built. If we recall, it has 9 engines on board. These 9 engines are more or less all the same, with the exclusion of the upper stage one. And there is a certain cadence which he has. So the question, and we'll see it in a second, is at which cadence of production will I get my minimum costs? This is another picture for Ariane actually, and you'll see indeed that the structure with all stage components also make quite a huge percentage of the cost of the launcher itself. So indeed, recovering stages is certainly something that we could engage in. Now, what is the effect of cadence and infrastructure on cost per unit? What you see here is on the y-axis the cost per unit, and what you see on the x-axis is the number of units produced. And of course, when you have just an increasing cadence, you will have something like this as a decreasing slope in terms of the cost per unit. Now, at a certain point, your manufacturing plant is not going to be sufficient for you to increase the cadence anymore, so you're going to have to invest again. You'll get a step increase in the cost per unit. And then if you continue producing further, then you'll have another decrease. So, and the same thing applies, of course, if we say the number of flights and the cost per flight. So, of course, from a SpaceX perspective, the question is, how much do I have to reuse so that I can stay in here without having this increase in infrastructure, and actually reduce this due to the fact that I'm actually reusing, because then that plot sort of gets divided by 2, for example, if I'm reusing twice. So another question is, but where are we in terms of in space? So we were talking about reusability of access to space. What about reusability in terms of in space, things that we could be doing in space? And for me there, we're even looking worse, of course, because of the simple reason that at the moment we have quite a catastrophic situation in terms of what debris is concerned. We've had some explosions, we've had some collisions. We've had one specific collision in 2009, which has significantly increased the number of debris in space in terms of fragments. And if we look at the numbers of, for example, catalogued objects as well, in terms of who is responsible for what, we will see that indeed, at least in Europe, we haven't produced that much debris. But in generally, there's quite a lot of debris up there, either in terms of satellites which are non-functional anymore. We're about, I understand, 4,500 satellites in space, and of these, only 1,500 are actually functional. So there's 3,000 non-functioning satellites in orbit, which are just flying around. And you see indeed here, we see the percentage of this total curve of actual spacecraft. And we have, of course, rocket bodies, and we have sort of mission-related objects, and then we have fragments. And what's scary, of course, is that this number obviously will increase further and further if we do nothing about it. So reusing in space will mean investing in infrastructure, but it will also mean to actually invest in cleaning up. This picture instead shows who is responsible for bringing these assets into space. And what we see is that whilst in the past we had lots of civil and sort of military activities from different countries, especially the US and Russia and the Soviet Union, what we see today is an increase of commercial activities. And this is something that we need to pay extreme attention to because of a certain number of reasons, which I'll go into in a second. Now, I think you've all heard about this, the Kessler syndrome. It just shows what will happen if we do absolutely nothing to resolve the situation of debris in space. And you'll see that the number of small particles larger than 10% will increase exponentially. Another picture that I want to share with you, because I found it quite scary, is what actually happens to fragments after sort of there's a sort of collision event. After a couple minutes, there's a small cloud. After a couple hours, the orbit is more or less ruined. After a couple weeks, orbital planes will have changed. And after a year, the whole sort of circumference of the Earth is covered with debris because there are perturbations in the conditions around the Earth, so that the fragments are not stable within one single orbit. This shows you again a picture of the objects which are larger than a meter, and it still doesn't look too scary. If you go to objects greater than 10 centimeters, it starts getting quite busy. Greater than 1 centimeter, greater than 1 millimeter. So there is much work to do. We've had several problems ourselves. In 2014, we sent up a Sentinel-1 spacecraft for Earth observation purposes. Again, one of those spacecraft that we need for infrastructure, as I was saying to you at the beginning, one of those infrastructure assets that we will need also in the future to enable those streams that we have. And in 2016, we discovered that there was a small impact on one of our solar arrays, which actually caused a little decrease in our power supply. It wasn't too bad. We could continue using the mission, but it's something that hit us very close. So even despite the fact that Europe doesn't contribute too much to producing debris, it's a problem for everyone. We have regulations, and this is, I apologize for the fact that it's in German, but I think you all can do it. But there's obviously bodies that try and regulate the fact that we don't produce any further debris. And there's several things that are said, of course, that these actual satellites shouldn't explode. They should the missions themselves shouldn't produce as much debris or waste while they go up. And if things go wrong, these things should happen at heights where the debris actually comes back down relatively quickly. And in any case, things have to be put in an orbit such that after 25 years they will re-enter themselves into the atmosphere. Unfortunately, this is not always the case. I mean, this is not actually done actively. We currently have a problem where these guidelines have been more or less agreed by each and every agency, but the actual implementation isn't happening. So now if I go back to this picture, which I shared to you at the beginning, showing what we have now in space and what will happen in the future, if we now take this 25-year rule and sort of apply it in the past, still, I must say, it doesn't look too good. So even the 25 years for me is not a solution. Indeed, I'm happy that we have the 25 years, but I think we need to be more proactive in addressing the problem. Now, the other problem we have is, of course, if we look at the orbital lifetime of objects, if we see, for example, at an altitude of 1,000 kilometers, the orbital lifetime is actually about 1,000 years. So these objects will stay in space forever, which is a bit of a problem, especially because at such altitudes we have some of our most important Earth observation activities and other activities going on. So it's in orbits that are extremely critical. Now, if you recall what I said to you before, that the amount of activities increasing are mostly commercial, now you'll understand why this picture sort of worries me a bit. Mega constellations, this is indeed what's happening. Space is becoming privatized, commercialized, and lots of new private entities are coming into space and investing into smaller satellites, investing into mega constellations that they will bring up to provide services for the future. Now, in some of these, you see right here, are pretty big. For example, OneWeb will have 720 satellites. Boeing are thinking of nearly 3,000 satellites. SpaceX thinking big, more than 4,000. Samsung 4,600. You see the orbits. There are orbits where indeed the orbital lifetime of debris is immense. So if something goes wrong, it will go wrong for a seriously long time. Now, just to add to the complexity of this, at this moment in time, we have a bit of a problem in our telecommunications sector. The number of telecom satellites which are being produced has gone down dramatically. And this is a bit of a problem for our producers. Now, the question that is raised is, can constellations replace lost geo revenues? And if we look at the cost and prices of one geo satellite, 5 tons about, and circa $150 million, and we compare it to CubeSats, then the conclusion is actually it doesn't. So the number of CubeSats that we would need to produce to provide the same service that is provided by a geosatellite doesn't make for the same revenue in terms of satellite manufacturers. And why is this a bit of a problem? It means that even the quality of the satellites produced cannot be the same. And indeed, what do people say? In these constellations, only about 90% of the satellites will be reliably functional. So now think back and think of 4,600 satellites in one constellation, and only 90% of these being actually functional. It means that 10% won't be. So it means there is going to be automatically, upon launch, upon the injection of these, there's going to be 10% of these which are not going to be functional. And who's going to take them down? Now think of the situation where these companies then go actually bankrupt. So, going back to reusability, recycling, how do we then consider, how do we think about even doing something which is sustainable, and then think of recycling and then reusing and being proactive in that? I was looking into trying to reuse materials which are on board of satellites, and I tried to calculate what happens if I take the value of the metals which are on board, both the precious ones and just the normal ones, and sort of compare it to the value of the processing or the cost of infrastructure required, or even the cost of access to space. And my result was it's not comparable. The metals are worth absolutely absolutely nothing. You can just chuck them away and re-enter it. So the question is, what do we do next? So both in the case of access to space, as well as in the case of reusability or recycling in space, what do we do? One of the questions is, do we go for just improvement measures? Do we do incremental approaches? Or do we do stepped disruptive approaches? Do we invest in some big SSTOs and put all our research into that? Or do we try and go for sort of stepwise improvement measures? And at least the answer I found is that we actually need both. We need both. So we have to have incremental improvement of chemical engines, the technology we have now, because we have to reduce the cost of access to space. And by just looking at SSTO, that's not going to happen fast enough. But at the same time, we have to look at disruptive solutions. And disruptive solutions, which in my view even go beyond just SSTO. And one of the concepts I was sharing with my students last Friday was, for example, beamed energy propulsion, where you sort of separate the energy source from the actual spacecraft. The other thing that, of course, we need to be doing is making sure that we have eco-design, that we sort of design clean satellites which will not explode once the batteries are empty, or where we have propellant no longer on board. So indeed, the solution is to look into in-orbit servicing. We have to do that now. We can't wait. And this will enable us to do assembly, transportation, satellite removal, refueling, inspection, and maintenance. And this is something that we're, for example, preparing. Arnold said that we're preparing the next ministerial. This is exactly something that we're doing actively. We've come to the conclusion that if we look at the removal of satellite from orbit, we will have to do certain things like inspecting it and rendezvousing it with it. We will have to capture it in some way. We will have to manipulate it in some way, not in perhaps fine manipulation that is required for payload exchanges, and we will have to target. And these are all functionalities that will be required for in-orbit servicing, for in-orbit production, and all these things that we've been speaking about. We are currently investing into technology development, both on the robotics side as well as from the avionics side, to make sure that we have those technologies ready for these things to happen. I must say, unfortunately, in Europe, we're not investing as much as in the US. It's about magnitude of an order of magnitude bigger what they've invested in the US so far in this, so our industry is certainly going to have a hard time. But we're pushing this forward. The other thing that we should invest into is collision avoidance automation, to make sure that our systems on board can automatically upload information from databases. So we need to be sharing data amongst the different databases worldwide, so that satellites themselves can decide if they have to sort of avoid another satellite or avoid a piece of debris. At the moment, we have people doing this, and with mega constellations, this is not going to be sustainable anymore. And then, of course, yes, we will have to start thinking of having recycling production facilities in orbit. I don't know how, but I put this to you. You're the young generation here, and you can sort of help me look at this both from a satellite point of view as well as in situ resource utilization and recycling of things that we produced. But this is not the end of the story. We also need some regulatory aspects. And when I started looking into this, I also thought, okay, let's look at what they've done for cars or airplanes. Cars and airplanes have been around for a while, so you'd expect there's something quite sustainable in place. And I was actually quite surprised to find out that the first regulation that came out on the end of life of vehicles was in 2005. This is not very long ago, but cars have been around forever. And it was the first time that the EU sort of made a waste directive where the Commission introduced the concept of extended producer responsibility. So the responsibility of the producer doesn't end by just sort of delivering the item, but it goes beyond. And it looks at reduction of waste from sort of cars that we, as normal people, have, by preventing the use of certain metals, by sort of recollecting these vehicles, by depollution of fluids and specific components, and then by introducing this reuse, recycling, and recovery performance targets. So, of course, the pledge is that we need the same kind of directive for space vehicles and assets, where we also perhaps introduce some concept of extended responsibility. But then the question is, how do we go about the rest? Do we introduce a tax on each and every launch? Do we introduce a tax on orbital slots? how do we go about it in such a way that it's actually sustainable? How do we go about it in such a way that even those manufacturers that have put up mega constellations and have gone bankrupt afterwards, there's still someone that can still remove that debris and well, make it commercially viable so that it's actually done. Because at this stage, the threshold is far too high, so it's not done. And then who should this entity be? We need to have commercial growth in the sector. It's not just a question of the public sector imposing this on producers and operators. It has to have some commercial outlook to it. Otherwise, it's not going to happen or it's not going to be sustainable. And then, of course, just to add as a picture to represent the political side, we need to have political support for all these things that we do. And this is one of the things that we keep on engaging in, at least in the preparation of the ministerial. And then with that, I come to an end, and I pledge you to, just like Wally, reuse, recycle, upgrade, and maintain.
Ja, ganz herzlichen Dank, Chiara. Ich glaube, es sind etliche Fragen da. Darf ich einfach gleich vergessen?
Okay, sort of a question. You talked about the space rider mission. When is the plan to actually start it and to be fully functional?
The space rider mission, 2026, well, 2025, 2026 we plan to launch it. So at the last ministerial we got phase A and B phases approved. At the next ministerial we want to ask for the C, D and E phases, which would go up to 2025. I must very openly, the hurdle we have there is that we're going to present a program called Space Safety at the next ministerial, and this program will contain not just space weather, it will have planetary defense and debris or in-orbit servicing as one of the topics. Surprise, surprise. And the problem there is we're going to have to make sure that we phase the missions properly so that member states don't kill one, if you will, in favor of another. So it's so-called famous phasing of missions.
Just one follow-up question. Is it only because ESA, the agency built it, is it also for commercial use or only for agencies and science and research and free flyer program?
It's not a science mission, so scientists can use the data. It's an agency finance mission, but it's not an agency asset. Well, it's going to be an agency asset, but the point is that we will have commercial services being provided with this mission. So it's an operational mission. We had a sort of a heads of delegations workshop on this, and one of the member states was very clear: it's not a scientific mission; it's an operational mission, which is important, of course.
I have actually two questions. There seem to be a lot of projects for reusable launchers within Europe right now. So you talked about Skylab, about the space radar. There's also Callisto and so on. I was wondering about ESA's policy of overseeing all those launchers. And also I remarked you talked about the Dream Chaser project.
Yes.
And I was wondering, ESA policy these days seem to be toward making European components. How does the integration of an American system goes in this policy?
Okay, so I'll answer your last question first. I sort of need to correct one of the things you said. You said it looks like ESA policy nowadays is to develop European components. But ESA's money comes from European member states, so it would be hard for ESA's policy to be take money from member states, run abroad, and invest into non-European companies. So just as a statement. So of course we invest into European industry, but we try and do collaboration worldwide, either by having common projects where we invest on an exchange fund basis, or through dedicated collaboration. And what concerns the Dream Chaser, we had different things going on. What they're trying to do, Sierra Nevada Corporation, is to launch this relatively soon, and and they're looking for a launcher to send them up at least 6 times. And they asked European industry whether it would be prepared to launch the Dream Chaser from Kourou in both its research version as well as its manned version. Now for the manned version it would be a little bit harder because we would need to have sort of all sorts of security and human-related aspects. With the research version, I understand there's a small problem associated with mice before launch, but I think these hurdles could be overcome. The issue there is, to be quite blunt, is the investment that European industry itself will make and the investment that ESA will make as an institution, as member states. What we're trying to push is actually to get more and more industrial responsibility in all of our sectors. So in telecom we see it. The projects are PPPs, where industry puts up to 75% of the money in the development of things, assets. In Earth observation we're getting this increasingly. In launchers it's a bit difficult, but we're also pushing for more industrial responsibility. So again, we'd be extremely happy to be able to sort of launch the Dream Chaser with IN 6. But again, it's a question of how much member states are willing to invest and how much industry sees this as a business opportunity and is willing to take money in its own hands to adapt, for example, the launcher for the Dream Chaser. So that's the policy. Now back to your first question, which I've now forgotten. Could you repeat your first question, please?
It was about the general policy for overseeing all the projects for reusable launcher or even devices in space.
So you're asking me what the policy in ESA is regarding reusability?
Yes, especially how they are in competition with each other.
Well, competition is a good thing. Competition means that industry is going to look at being the best, and we want industry to be the best. We don't want monopolies. So competition is a good thing. Of course, if we stay within Europe, again, competition is not a problem, and it's actually very good. If we now look outside of Europe, and then we ask ourselves, why do we need launchers? Then competition starts becoming also a hurdle or a difficulty. If we see launchers to be something that we need strategically because we have to be able to launch our institutional missions, then we we might have to be prepared to invest to make sure that we might be competitive on the commercial market. So, as I said before, reusability in and of itself, this is my personal opinion, cannot be an aim. As an engineer, I will tell you, yes, reusability is fantastic. It's super cool. We must do it. From an industrial point of view, reusability cannot be an aim of its own. It has to be geared towards either being competitive or having competitive launcher prices or something of the sort. So we are looking into it. So it is in our current portfolio of activities. You've mentioned Callisto. IAN's group has put forward concepts with Adeline, where they want to recover just the engine base. So there's many concepts. The question is, will it work for our European launchers? If we look at Ariane, we have one engine and one central stage. And if we say we use the central stage and engine 6 times or 2 times, then it means we're not producing it 6 times a year. The Ariane 5, we're producing it only 3 times a year. Then the question is what's going to happen to the price, because we have to still maintain the infrastructure cost on that reduced number of cabins. So again, the policy is any technical advancement which will make us competitive and on top looks cool is something that we're happy with, and if there's competition, then that's fantastic.
But isn't there a risk of spreading funding by investing in too many projects?
Now this is the sort of a chicken and egg question. I believe, and I tell you, Arno told you I'm sort of helping with the preparing of the next ministerial conference. And I think we can get always more money if we're better at explaining what we do and why we do it. So I think that when we end up posing this question, it's because perhaps we weren't good enough at telling people what we're doing. So I'm not answering your question, I'm giving you an alternative reality.